Welcome back, design junkies, to Mechanical Engineering Made Simple. If this show brings you value, help support it with a like, a follow, or leave a comment below.
You know the feeling. We've all been there. You spend weeks, maybe months, just perfecting a design. The drawing looks absolutely flawless. You ship it off to be made, the part comes back, it goes to inspection, and boom, passes with flying colors. Then it gets to the assembly line and it doesn't fit. How in the world does that happen? How can a part that meets every single specification on a drawing fail when it matters most? Honestly, it's one of the most frustrating and expensive problems in engineering. Okay, let's dive right into this. The answer, believe it or not, lies in one of the single biggest misconceptions in all of geometric dimensioning and tolerancing, or GD&T. It turns out we have a fundamental misunderstanding about the relationship between a design drawing and how you actually measure the part.
Yeah, see, we're taught to see the engineering drawing as the absolute Bible, that it tells us exactly how to measure and verify a part. But it really doesn't. A drawing's job is to define what is required for that part to function correctly. The how? Well, the how of measuring it is a completely separate thing. That has to balance all sorts of business needs like cost, time, and of course, liability. So when you look at a drawing that's based on the ASME Y14.5 standard, that's the American Society of Mechanical Engineers, you're looking at the rulebook for the final product. It defines the required tolerance zones. You can think of them as these perfect geometric boundaries that the real-world, imperfect part has to fit inside. It's the goal line. It's the ideal. Now, on the other side of that gap, you've got standards like ASME B89.7.2. This is all about dimensional measurement planning. This is the playbook for the inspection team. It helps them figure out a practical strategy to actually go and verify those design requirements, but in a way that makes sense for the business. So here's the crucial takeaway. You cannot conform a measurement method to Y14.5. The standard itself says, flat out, it is not a gauging standard. It only defines those perfect tolerance zones. Any number you get off a CMM machine or a pair of calipers, that number is the result of a whole bunch of assumptions that go way beyond what the design standard actually says. Confusing the design requirement with the measurement plan, that is the root cause of so many arguments and so many bad parts. All right, now if that wasn't complicated enough, let's get into the next major headache that makes everything we just talked about even trickier. And that's the fact that the entire engineering world is basically trying to speak two different languages at the same time. And this slide pretty much sums it up. Here in the United States, we mostly use the ASME Y14.5 standard, but pretty much the rest of the world uses the ISO standard, specifically 1101. Now, here's the wild part. Back in the 90s, these two standards were like 90 to 95% in agreement. They were almost the same thing, but they've been drifting apart ever since. Today, some experts figure that alignment is down to maybe 65%. That growing difference means more risk, more cost, and a whole lot more confusion in our global supply chains. And this right here, this is a perfect and frankly painful illustration of the problem. What you're looking at is the feature control frame for concentricity. Okay, so under the ISO standard, this symbol controls the central axis of the feature. Simple enough, right? But under the ASME standard, it controls the median points of opposing sides of the feature. It's a subtle difference on paper, but it's a profound difference in reality. The same exact symbol means two completely different things. You can just imagine the errors that can cause when a part designed in the US gets made in Europe or Asia. Okay, next up is a problem that can just silently destroy an entire assembly, even when every single little component is perfectly within its own specification. This is the silent killer we call tolerance stack-up. So the classic way to deal with this is something called worst-case analysis. It's pretty much what it sounds like. You do all the math assuming every single part in your assembly just happens to be made at its absolute worst possible dimensional limit, and all at the very same time. Now, this method is totally bulletproof. It guarantees your assembly will fit every single time. The big downside? It often forces you into specifying incredibly tight and therefore incredibly expensive tolerances. The more modern way to do it is with statistical tolerance analysis. Instead of assuming the absolute worst, this method is smarter. It knows that manufacturing variations usually follow a probability curve, like a bell curve. It's just extremely unlikely that all your parts will be at their worst limit at the same time. So this lets you open up your tolerances, which makes the parts way cheaper to produce.
The trade-off, of course, is that you're accepting a very small, calculated risk that a tiny percentage of assemblies just might not fit. Okay, we've gone through some of the big systemic challenges. So now, let's switch gears and get into some practical advice to help you avoid some of these common mistakes on your own drawings.
This right here is the golden rule, seriously. There's this natural urge for designers to just tighten up tolerances to be safe. But you have to remember, every tightened tolerance adds cost, and sometimes it's exponential. Your job as a designer isn't to make the tightest part possible. It's to define the loosest possible tolerance that still lets the part do its job. Anything tighter than that is just throwing money away.
And this is a perfect example of a mistake that seems subtle but is actually critical. You've got a simple radius callout with a plus or minus tolerance. Seems fine, right? But it's a trap. In the ASME standard, what this does is create a tolerance zone that actually tapers down to 0 right where the curve blends into the straight lines. This ambiguity makes it almost impossible to measure reliably and repeatably. Different inspectors are going to get different results, and it's all because the callout itself is just poorly defined from the start. All right, to pull all of this together, let's do a quick fire round to clarify some of these core concepts we've been talking about. Because honestly, getting these terms right is the foundation for avoiding all the mistakes we just went over. First up, basic size. This is easy. Just think of it as the theoretically perfect dimension you have in your CAD model. It's the ideal target you're shooting for, before we even start thinking about all the messy real-world manufacturing variations. Next, allowance. This is the intentional space you design between two parts that have to fit together. It's the minimum gap you want for a loose fit or the maximum overlap for a tight press fit. This is the space you plan for on purpose. And then there's tolerance. This is the unintentional but acceptable amount of variation you can have on a single part. It's the very core of what we've been talking about. It's just accepting the reality that nothing can be made perfectly, so we have to define an acceptable range of imperfection to manage cost and function. And finally, all of this comes together to create the fit. The fit is simply what you get, the tightness or the looseness, when you actually assemble two parts. It's the real-world result of your planned allowance and those unplanned but controlled tolerances. So when you really think about all these challenges, the measurement gap, the tolerance stack-ups, the common design mistakes, every single one of them gets magnified by that great standards divide we talked about. And that really leaves us with a final and I think crucial question. In our modern world of global manufacturing, can we really afford to have two different and diverging engineering languages? If you got something useful out of what we covered today, hit follow and drop a like. It helps grow the show and keeps the engineering knowledge flowing.